We are Team 23. We are presenting a machine learning project on lung cancer prediction. We have developed and evaluated several models to predict pulmonary disease risk based on demographic factors, lifestyle habits, and medical symptoms. This work has important implications for early detection and screening prioritization. Here's what we'll cover in today's presentation. I'll start with an overview of the project and dataset, walk through our exploratory data analysis, explain our modeling approach, present our results and sample predictions, address challenges, and conclude with future directions. Let's begin. Our primary objective was to build a predictive model for pulmonary disease using a dataset of 5,000 patient records. Each record contains 18 features spanning demographics, lifestyle factors, and medical history. Our target variable is binary, whether the patient has pulmonary disease or not. We've implemented 5 different machine learning models and evaluated them using standard metrics, including accuracy, precision, recall, and F1 score. This approach allowed us to identify the most effective model and understand which risk factors are most predictive of pulmonary disease. Our dataset comes from Kaggle and consists of 5,000 records with 18 features. These features fall into several categories: demographic factors like age and gender, lifestyle habits such as smoking and alcohol consumption, medical measurements including oxygen saturation and energy levels, patient history including family medical history, and various symptoms associated with pulmonary disease. Importantly, our dataset was complete with no missing values, which specified our pre-processing steps and increased our confidence in the results. Let's look at our exploratory data analysis revealed. The age range of subjects spans from 30 to 84 years, with a mean of 57.2 years. Gender distribution is nearly equal to at 50.1% male. Some key statistics stand out: 66.6% of subjects were smokers and 80% reported breathing issues. The average oxygen saturation was 95%, which is within normal range but on the low end. Energy levels averaged 55 on what appears to be 0 to 100 scale. This initial analysis gave us a solid understanding of our study population before we moved into modeling. It also highlighted potential relationships between features in our target variable that warranted future further investigation. When we separated our data by the target class, those with and without pulmonary disease, several striking differences emerged. The most dramatic difference was in smoking status. 92.9% of those with pulmonary disease were smokers compared to just 48.6% of those without. This immediately suggested smoking would be a powerful predictor. Throat discomfort was present in 85.5% of positive cases versus 59% of the negative cases. Breathing issues showed a similar pattern: 93.1% in positive cases versus 71.1% in negative cases. Interestingly, energy levels were actually higher in positive cases, 56.7 versus 53.9, which was somewhat counterintuitive and worth further investigation. Family history of smoking was over 3 times more common in positive cases at 35.1 versus and 10.3 in negative cases, suggesting a strong genetic or environmental influences. For our methodology, we split the data with 80% 4,000 records used for training and 20% 1,000 records for testing. We encoded our target variable where no became 0 and yes became 1. We implemented 5 different classification models. First one, Logistic regression, which is interruptible and works well for binary classification. Second, decision tree, which captures non-linear relationships. Third, random forest, which reduces overfitting by ensemble learning. 4. Support vector machine, which is effective at finding complex decision boundaries. 5. K nearest neighbors, which makes predictions based on similarity metrics. This diverse set of models allowed us to explore different approaches to the classification problem and identify which perform best for a specific data set. For initial model training, we focused on optimizing our best performing model, which was random forest. We conducted hyperparameter tuning, optimizing for the number of trees in the forest, the maximum depth of each tree, the minimum samples required to split a node, and the minimum samples required in a leaf node. We also performed k-fold cross-validation for all the models to ensure robust evaluation and to check for overfitting. This process helped us to understand how our models would perform on unseen data and whether our results were stable across different subsets of the training data. Now for our results, this table shows the performance metrics for all 5 models. Random forest achieved the highest accuracy at 90.4%, followed closely by SVM at 88.9% and logistic regression at 88.7%. KNN and decision tree performed somewhat lower at 85.1% and 80.5% respectively. Looking at the position for the positive class, which tells us how many of our predicted pulmonary disease cases were actually positive. Random forest again leads with 0.89, meaning 89% of its positive predictions were correct. Recall for the positive class, which tells us what proportion of the actual positive cases of our model identified, was highest for logistic regression at 0.88, with random forest very close at 0.87. The F1 score, which balances precision and recall, was the highest for random forest at 0.88. Overall, random forest emerged as our best performing model across most metrics, which is why we selected it for further optimization. Our cross-validation results confirm the stability of our models. Random forest maintained the highest accuracy at 91.0% with a standard deviation of 1.4%, indicating consistent performance across different data subsets. Logistic regression showed impressive stability with 89.9% accuracy and the lowest standard deviation at 1.0%. SVM performed similarly at 88.8% with 1.3 standard deviation. KNN and decision tree showed lower but still respectable performance at 85.9% and 83.2% respectively. Though KNN had the highest variability at 2.1%, after hyperparameter turning for random forest, we found the optimal configuration used 50 trees with a maximum depth of 10. This tuned model achieved a slight improvement in across validation accuracy to 91.2% and test accuracy of 90.3%. The minimal improvement suggests our initial model was already well configured. Rate how our model works in practice. Let's look at some sample predictions. Here we have 5 cases with their features and models predictions. Case 1 shows a 53-year-old smoker with throat discomfort but good oxygen levels and no breathing issues. Despite the smoking status, our model classified this a low risk. Case 2 is particularly interesting. A younger smoker at age 36 with family history and multiple symptoms predicted as high risk with 79.9% probability. Case 5 shows another high risk prediction. 82.7 probability for a younger smoker with good energy levels but multiple symptoms. This example demonstrates how the model weighed multiple factors together rather than relying on a single indicator. Our analysis yields several important insights. First, smoking remains the strongest predictor of pulmonary disease, which aligns with established medical knowledge. The unexpected importance of energy levels suggests that subtle psychological changes might precede more obvious symptoms, potentially offering earlier detection opportunities. The combination of throat discomfort and breathing issues emerged as strongly predictive when present together, which could help prioritize diagnostic testing. Family history of smoking adds significant risk beyond personal smoking habits, highlighting potential genetic susceptibility or shared environmental exposures. From a clinical perspective, our model demonstrates a strong potential for early screening prioritization, potentially allowing medical resources to be focused on those at highest risk while requiring only readily available data. Conclude, a random forest model achieved 90.4% accuracy in predicting pulmonary disease risk, with smoking, energy level, and specific symptoms emerging as key predictors. For future work, we recommend incorporating more detailed symptoms, severity data, and evaluating model performance on external datasets to confirm generalizability. Developing a specified clinical scoring system based on our findings could make these insights more accessible in clinical settings. Finally, investigating the temporal progression of symptoms could further enhance early detection capabilities by identifying the earliest predictive signals of pulmonary disease. Thank you.